Good morning.
Good morning.
Okay. So in last class, we talked about radioactivity, certain fundamentals of radioactivity. Now, before proceeding with further discussions on radioactivity, let's have a recap on what we learned in last class. So, radioactivity means the it is a nuclear phenomena, and it happens because it is associated with spontaneous emission of various types of radiation such as alpha, beta, gamma, and other types of radiations from a nuclei. Now we have radioactive decay law. So this radioactive decay law is actually, the law is first, it follows the first order kinetics that we have seen, and the discovery of radioactivity, it was by Henry Becquerel. The first law of radioactivity, it says that it follows the first order kinetics, and it says that the rate of disintegration of any radionuclide, it is directly proportional to the number of atoms that has been present during that time. And from the radioactive decay law, we have the equation of T half, that is calculation of T half, that can be done as ln 2 by lambda or 0.693 by lambda, where T half, it indicates the half life of the radioactive nuclei. And we also have the radioactivity second law that was proposed by Soddy, which tells us about the position of the dotted nuclei that is formed after the radioactive decay. According to this law, when the parent, it emits an alpha decay, it undergoes an alpha emission, then the Z is decreased by 2 and it is displaced to 2 position left in the periodic table. And when a parent nuclei, it emits a beta emission, then the Z is increased by 1, and the new daughter element that is formed, it moves one position right to its original position in the periodic table. So this is the law of displacement, group displacement law, that is proposed by Soddy. Then coming to units of radioactivity, the most common unit that we use for to describe the radioactivity of material is mostly in Curie, and that is given as Ci. There are other units like DPS, disintegrations per seconds, or becquerel. However, we mostly concern with the unit Curie and represented as Ci or MCI, which implies millicurie. Now, we have also studied about natural radioactivity. So natural radioactivity, it indicates the elements which are naturally radioactive in nature, such as uranium 235 and uranium 238, also thorium 232. It is a natural radioactive element. So based on the natural radioactivity of various elements, there is a decay series which have been labeled as 4n, 4n plus 2, and 4n plus 3 series, depending on the type of the emission. So the natural radioactivity decay series of 235 is called as, it is also called as 4n plus 3 series. The 4n plus 2 series, it is given by it is given by uranium 238, and the 4n series of radioactivity is given by thorium 232. So we had also studied about the classification of various types of nuclides. So first group is the stable nuclides that are found in nature and they do not undergo any type of radioactive decay. The second groups are the primary natural radionuclides which are found in nature and they have very long half lives, like that of uranium 238, which has a half life of 4.5 into 10 to the power 9 years. Then the third category is the secondary natural radionuclides, which are found in nature as a decay product of the primary natural radionuclides, and their half lives are quite short. For example, we have radium, that is 226, and thorium 234. The half life of thorium 234 is 24.1 days, and these are all the decay products coming from uranium 238. Then the fourth category is the induced natural radionuclides. So they are actually continuously produced by the action of the cosmic rays on the atmosphere of the earth, and hence these are you can mostly found in nature. Now two of the very commonly known induced radionatural nuclides are H3, that is tritium, whose T half is 12.3 years, and carbon 14, whose T half is 5730 years. And both these elements or both these nuclides, they are used for radioactive dating. The fifth and final category of radionuclides are the artificial radionuclides. They are produced by the bombardment of nuclear particles on a target nuclide, and hence they are not found in nature. So, this is artificially induced, and the reaction is mostly carried out in a nuclear reactor. And more than 2000 such nuclides have been reported till date. So this is a common classification of radionuclides. We have also classified radionuclides on the basis of their atomic number, that is Z, and their mass number A, and also considering the neutron number. So the first class is the isotopes. The isotopes are the set of nuclides where the Z is the same but they have different mass numbers. Like for example, we can consider the case of hydrogen, which has three isotopes: 1H, 2H, and 3H. Among this, the 3H is radioactive in nature. So the next is isobars. Isobars are the nuclides where the A remains the same, that is the mass number remains the same, but the atomic number is different, that is their Z is different. Like we have example of 12B, 12C, and 12N. They all have the mass number is same for all these three elements, however their atomic numbers are different, that is the number of protons are different in these cases. There is another class of nuclides which are called as isotones. Isotones are particularly those nuclides where the number of neutrons are the same but the number of protons are different. For example, if we consider carbon 14 and nitrogen 15, so in both these cases they all have 18 neutrons. That is the number of neutrons, 8 neutrons, that is the number of neutrons remains the same but the number of protons are different for these three elements. We also have nuclear isomers. So these nuclides, they have the same Z and A, but they have different nuclear excitation states, and they are designated using small m. Since their metastable state is different, we designate is them by the nuclear isomers are designated by the small m. Like for example, bromine 80 and bromine 80m, they are nuclear isomers of each other, which means that the bromine 80m, it indicates that it is in metastable state. So this is a nuclear isomer. So or we can say that one is the isomer having nuclear isomers, that is has a different half life than the parent isomer, parent nucleus. Then coming to the concept of isotopic and relative atomic masses. So first, before understanding this, what is a relative atomic mass, we need to consider a few certain factors. Like we all know the mass number A. Mass number A is always the sum of Z plus N. That is, it is the sum of its atomic number plus the number of neutrons that is present in the nucleus. That is, mathematically, as it is shown here, we can write A is equal to Z plus N. Now, the nuclear mass, or we call it as the isotopic mass, however, most commonly it is called as the nuclear mass, and it is represented as M with a subscript A. So, it refers to the mass of one atom which is expressed in atomic mass unit, that is AMA, or we call it as a Dalton. That is, we can write it as 1 AMU is equal to 1.66 into 10 to the power minus 27 kg. This equals to 1 Dalton, and which further is equal to 931.5 MeV, where this MeV, M here it represents million electron volts. That is of the order, we sometimes it has been referred to as mega electron volt, but mostly in common notation we say it as million electron volts. So here, looking from this part, we find out that 1 dalton is equal to 1.66 into 10 to the power minus 27 kg, which equals to 931.5 MeV. Now, the isotopic mass is calculated from this equation by considering the mass of the proton, which we know that the mass of the proton is equal to 1.007823 AMU, and also we need to consider the mass of the neutron, which is 1.008665 AMU. So here, supposing, let us calculate the mass of sodium 23. So if we look into 23 sodium, we know that it contains 11 protons and 12 neutrons. So the total mass of sodium can be written as 11 into the mass of proton plus 12 into the mass of neutron, which gives us this AMU. So this is how we calculate the MA, that is called as the nuclear mass. So now, coming to calculation of the relative atomic mass, the relative atomic mass, it actually refers to the average of all the masses of the naturally occurring isotopes in a particular element. So like for example, let us consider carbon. Carbon has two naturally occurring isotopes, that is C12 and C13, and their abundances in the atmosphere is given as 98.89 for C12 and 1.11% for C13. So therefore, the relative atomic mass, that is AR, of carbon is given as 12 into 98.89% plus 13 into 1.11%, and the average it gives 12.011. So from this value, this 12.011 is called as the relative atomic mass of a particular element. So this is how we calculate the relative atomic mass. Now, while calculating the mass, we also come across a very common term that is called as mass defect, and that is represented by delta M. So it indicates the difference between the mass of the nuclide and the mass number, that is Ma minus A of a particular element. Like for carbon 13, delta M, that is the mass defect, is given by this much AMU. So and particularly this is considered by calculating the nuclear mass of the element minus the atom mass number of the element. Okay. So these are certain examples that have been shown to you. Then now coming to artificial radioactivity. So we all know radioactivity, it occurs naturally from certain elements which are naturally they emit various type of emissions and radiations. But the artificial radioactivity, it is a type of induced radioactivity. So first, when natural activity radioactivity was discovered, then people thought of in artificial radioactivity and various efforts were made. So in 1999, Rutherford first he produced nuclear transmutation by bombarding this alpha particles, that is represented by He4 on nitrogen atom, and he found out O7 species was formed from this reaction. However, this O17 species that was formed, it was found not found to be radioactive in nature. Then in 1934, Irene Curie, who is the daughter of Marie Curie, she discovered artificial radioactivity by bombarding alpha particles on an aluminium foil. After this reaction, the product obtained, that is 30P, it was found to be radioactive in nature, and it became the first artificially produced radionuclide in nature. So this, the credit of discovering artificial radioactivity goes to Irene Curie, which who is the daughter of Marie Curie, whereas the credit of first discovering natural radioactivity goes to Marie Curie, who discovered naturally occurring radioactive substance. Now we need to know about certain nuclear reactions. Nuclear reactions actually proceeds similar to that of a chemical reactions. However, we need to consider certain factors, and the writing of a chemical reactions, nuclear reaction is a bit different than those meant in conventional chemical reactions. So nuclear reactions, Mainly, they happen to produce radioisotopes. So, when a nuclear reaction is a process in which the target nucleus is first, it is bombarded with a nuclear particle called as projectiles, which may be a neutron, proton, alpha particle, and it is then the projectile, it reacts with the parent nucleus to form a another element, and plus and it emits another particle that is called as a ejectile, which is given as E. So interaction of a nuclear particle has been known, it may either lead to scattering of the projectile, excitation of the target nucleus, or other gain or loss of other subatomic particles. So typically we may write a nuclear reaction to be this: if T is the target nucleus having mass number and atomic number A1 Z1. So B is the projectile, that is it is the target nucleus is bombarded with a projectile B, give it with having a mass number and atomic number as A1 dash Z1 dash. Then the reaction proceeds to form the product P with A2 Z2 plus a particle is emitted that is called as ejectile, having mass number and atomic number as A2 dash Z2 dash. This is how a typical nuclear reaction is represented. Now in general, if we look into the equation shown in the writing of a nuclear reaction, one basic fundamental law that needs to be considered is the conservation of both A and Z in the reactant side and in the product side. Like that is, which implies that if you look into the equation in 12.6, Z plus Z1 dash should be always be equal to Z2 plus Z2 dash. That is the proton number, it should be conserved. Similarly, a1 plus A1 dash should be equal to A2 plus A2 dash. That is, the mass number should also be conserved. So, this is the fundamental of a nuclear reaction, that both the atomic number and the mass number that should be conserved, as it is shown here. Z1 plus Z1 dash is equal to Z2 plus Z2 dash. That is, the A and Z on the left hand side must be conserved with that A and Z in the right hand side. So now at this stage, we need to know how a nuclear reaction it differs from a chemical reaction. Now in most cases, in a nuclear reaction, a new type of isotope of the same element is formed, and it depends upon the type of the reaction. The energy involved in a nuclear reaction is called as its Q value, and it is very much larger than that is represented by a chemical reaction. In a chemical reaction, we represent the energy in terms of delta H, whereas in a nuclear reaction, it is represented as Q value, and it is much higher than that of delta H. Now, in nuclear reaction, it is never affected by temperature, pressure, concentration, and other reactions. However, in conventional chemical reactions, we know that these parameters highly influence the nature of the chemical reactions. Now, extranuclear electrons, they do not participate in a nuclear reaction. If different isotopes they are used as target material, then different products are formed. Whereas in a particularly in case of a chemical reaction, the products always remain the same. In nuclear reaction, it is represented in a different manner in comparison to a chemical reaction. The energy, mass number, proton number, and momentum are always conserved in a nuclear reaction. In nuclear reaction, it is performed in a nuclear reactor, or we call it as an accelerator, while a chemical reaction might be performed in a test tube, a beaker, or a RB in a normal chemical laboratory. So also in case of a chemical reaction, the total number of atoms on each element on both sides is conserved. That is what we call it as the balancing of the chemical equation. However, in a nuclear reaction, it is the total number of nucleons. That is the total number of protons and neutrons on both the side. It is conserved. This is a very crucial factor. Primarily, a chemical reaction it takes place on a molecular basis, whereas if we look into a nuclear reaction, it occurs on an atomic basis and it deals with the nucleons, that is the number of the protons and number of the neutrons. Now, this is some of the differences between a chemical reaction and a nuclear reaction. Now, we look into the type of energy that is involved in a nuclear reaction. So, since we call a nuclear reaction is involved in energy changes, it is called as Q. The change in energy in a nuclear reaction is called its Q value. It is which is represented as delta H in conventional chemical reactions. Now here, if the Q value is negative, then the reaction is called as endoergic in nature. That is, the energy is absorbed in the form of an acceleration to the bombarding particle. On the other hand, if Q is positive, then the reaction is called as exoergic in nature, and this is the reaction is carried out without acceleration or at thermal temperature. So the value of Q, this Q value, it can be determined from the difference in total masses of the reactants and products, which is given in this equation. This particular value of 931.5 is it comes from the value of the million electron volts that we have studied earlier. So now this Q is calculated from the summation of the mass of the product of the reactant side minus the summation of all the mass in the reactant product side into 931.5. An example has been shown here and it illustrates the how to find out the Q value. And the Q value here, the unit it comes out is MeV, that is million electron volts, since much higher energy is used in a nuclear reaction. So now in the example 3, it has been shown that the how to calculate the Q value. So now we all know these there needs a certain amount of energy that is needed to carry out the nuclear reaction, and this is called as the threshold energy, similar to that of a chemical reaction where we call it as the threshold energy to induce the starting of a chemical reaction. This minimum amount of energy that we need to carry out a nuclear reaction is called as a threshold reaction. This threshold energy is equal to the Q value of the endoergic reaction plus the amount of the additional energy needed to conserve the momentum and to overcome the Coulomb barrier. So for an exoergic reaction, there is no need of threshold energy because the reaction can start on its own. An exoergic reaction may be carried out as a thermal energy. So another important parameter that needs to be considered for nuclear reaction is the nuclear reaction cross section, which represents the probability that a given nuclear reaction will occur. This nuclear reaction cross section is denoted by the letter sigma. So for each reaction and a given energy of the projectile, the reaction cross section, it is determined from the reaction yield, the known surface density of the target nuclide, and the projectile flux, that is the number of projectiles that is bombarding the target nucleus per second square per second. So if a nucleus of radius r, it represents a target area of pi r square, then the incident particle that will strike the nucleus, it is directly proportional to the area of the target. So in general, nuclear reaction cross sections are almost the same magnitude of that of the target area. So the unit of cross section is bar, which is represented in small b, and it corresponds almost to the value of 10 to the power minus 24 centimeter square. So by assuming that the reaction is possible only if the projectile passes through the surface area of pi r square, we get sigma is equal to this much value. So when we consider a nucleus of average mass A is equal to 100, then the sigma comes to be of the order of 10 to the power minus 24 cm square. However, the sigma has experimentally has been determined at target nuclei, and various other projectile area has been reported in literature. So further different kinds of reactions may occur depending on the energy of the bombarding particle with the emission of different types of particles. So here if we imagine the total cross section of this reaction at any energy to be sigma, which will be equal to the sum of all of the different reactions occurring due to sigma, that is sigma is equal to sigma 1 plus 2 plus the summation of all other sigma. So the production of activity of radionucleotide, that is the activity, it indicates the number of disintegrations that occurring per second. So that is, as a result, this activity, the activity of a radionucleotide, we know it is directly proportional to the number of target nuclide on an element in the sample. It also depends on the number of the bombarding particles. It also depends on the nuclear reaction cross section, that is given as sigma, and the time of radiation. Thus the activity of combining all these factors, the activity of a radionuclide is given as this, that is n phi sigma t, or we can write it as wi by m into phi sigma t. So this is especially the case where the half-life of the products of the nucleus is very large compared to irradiation time. So activity is given by this equation. Now coming to some commonly used radioisotopes. Now there are hundreds of isotopes that have been used in various types of physicochemical and biological investigations. Now these radioisotopes, they are actually available in solution from a very common, we can get them from the board of radioisotope radiation and isotope technology, that is BRIT in Mumbai, which provides these isotopes in solution. The BRIT also, it provides the half life, nature and energy of the radiation of the radioisotopes that has been brought from them. So here in table 12.3, some of the characteristics of commonly used radioisotopes have been listed. As you can see, this is 76As. The chemical form is sodium arsenide and it is present in NaOH solution. It emits gamma radiation. The energy of the radiation is 559 kilo electron volts, sorry, and the half life is 26.3 h, and the concentration is 1.5 millicurie. So this is the sum of the commercially available radio tracers or radioisotopes we can get in BRIT Mumbai. So that it is listed in, and for their availability form, their radiation, their energy, their half life has, it can also be found in the with them. So half life, which are designated by Y, D, H and MS, it stands for, Y stands for year, D indicates days and H indicates hour respectively. Now coming to preparation of radioisotopes and labeled compounds. So radioisotopes, initially radioisotopes were isolated from the naturally occurring radioactive elements such as uranium and thorium. Now however, in 1913, so the first isolation of radioactive an isotope was done from Pb 210, and it was used for determination of solubility of PbSO4. Then extensive efforts were made to isolate radioisotopes, and the further the, for, the further processing and the further studies have indicated some major developments in this area. Now, particularly in India, the sole supplier of radioisotopes is BRIT, that is Board of Radiation and Isotope Technology in Mumbai. So these are made by neutron irradiation in a nuclear reactor. The nuclear reactor might be, the name is Apsara and Circus at the Bhabha Atomic Research Center, that is BARC, Mumbai, and they are processed by the isotope group which is present in BARC. So most common method of preparing radioisotopes is by that is mostly it is done by neutron irradiation. So we will be coming to this topic later. Some commonly used isotopes that have been much, they are much demand by chemists are cesium 137, iodine 131. They have been first produced from the fission products of uranium in the nuclear reactor. So in some cases, particularly for research purposes, charged particle irradiation at VEC Calcutta, that is Variable Energy Cyclotron, that is present at Calcutta, and Pelletron facility at TIFR, Mumbai. They are also being used to produce other radioisotopes. However, for specific radioisotopes, we are dependent on other countries. India produces the listed isotopes above, and however, specific are procured from outside. Now, detection and measurement of radioactivity. So, detection of nuclear radiations that are emitted by radioisotopes, it depends upon the type of radiation that is used, the energy of the radiation, and the nature of the material with which the radiation interacts. So therefore, the measurement of the radioactivity is done by a particular instrument, and that instrument must meet the following criteria. That is, there must be a strict proportionality between the number of photons or particles that interacts with the detector, and subsequently it should also indicate the number of pulses that is generated, and there should be a linear relationship between the energy of radiation and the amplitude of voltage, which we call it as the pulse height. So now there are very three common most used detector systems for radioactivity. One is called as the gas ionization detector, the second is the scintillation chamber, and the third is called as the semiconductor detector. So among all these methods, that is all these processes, the scintillation method has been used, it has been mostly used, and we shall come to read in details about it. So starting with gas ionization detector, so these were the earliest detectors. So initially they were the primary detectors to be used for the detection of various types of radiation. Now here, when a radiation it passes through a gas, some of its energy is deposited on the gaseous molecules, and they ionize to form positive ions and electrons. So if we apply a suitable electric field here, the electrons or the ions that have been formed, they generate a pulse that can be related to the amount of radiations responsible for ionization. So supposing here a gas ionization, here in figure 12.7, a block diagram of a typical gas ionization detection has been shown here. It consists of a cylindrical tube that is filled with a non-conducting inert gas such as either argon or xenon, and a central wire which acts as the anode. The metallic wall of the cylindrical tube, it acts as the cathode. When the typically it is the connection has been shown in figure 12.7. When an ionizing nuclear radiation it passes through this window and interacts with the gas producing ion pairs, these ions are collected by respective electrodes. Now as a result, a voltage is produced, pulse is produced, and then this is measured. So actual detector here, it is made up of a conducting material with an electrically isolated central wire. So a very thin window which is made up of particularly of aluminium or beryllium. Here it is provided at the end of the detector, and a quenching gas is also provided. So here a continuous flow of the gas is maintained, and it measures the number of the pulses that is generated at the end of the ionization chamber, and that is what we measured in the timer counter. So in the absence of any radiation, so if no radiation is passed, then no ion pairs are formed, and hence no current passes through the tube. So when the voltage is applied across the central wire and nuclear radiations enter the tube, the ion pairs are formed and current passes through it. So as the voltage is increased, the number of ion pairs that are formed, that also subsequently increases. Now if we plot a graph versus plot a graph of number of ion pairs versus the current, the voltage applied, then we get a graph that is shown in figure 12.18. So here in x-axis the voltage is plotted, and here the pulse height is measured, and we can see various the function it shows as a function of this particular graph has been divided into six parts on the basis of the three types of detectors which differ in the magnitude of the voltage applied. So these are ionization chamber, proportional counter, and GM counter, that is called as Geiger-Müller counter. So each of these counters or chambers, they are particularly specific for specific applications. So if we look into 12 Figure 12.8, let us assume that after we apply a certain voltage, a single particle of radiation, it enters the detector through its window and it produces n number of ion pairs. So during this process, all of the energy of the particle is lost. Further, if the voltage applied is very small, then only a fraction of these ion pairs it will reach the electrode and the other will remain undergo ion recombination. So this region of V is equal to 0 to V1 is called as the region of ion recombination, and it is of no use because it does not detect any ion in this process. So, however, if the voltage is increased to an extent such that V is greater than V1, then the number of ion pairs it do not increase, but it also remains somewhat constant. So for voltages between V1 and V2, ion pairs formed remain constant and no secondary ions are formed. So and particularly in the voltage region, this V1 to V2, this region is called as ionization chamber detector, and particularly ionization chamber detector, it measures alpha and beta particles, and this was particularly primarily done for measurement of radioactivity. Now when we increase the voltage beyond this region, that is shown beyond V2, we can find the electrons, they will be subjected to a large electrostatic field, and thus the region between B2 and B3, the total number of ion pairs that reaches the electrodes, it increases, and it is this region is called as the proportional counter. This region is not only useful for measuring energy radiation, but it also discriminates between different radioisotopes that emits different types of radiations. So when the applied voltage is further increased, the electrostatic field becomes so large that a chain reaction results, and between the ionization particles, there a chain reaction results, and the proportionality between the energy of radiation and the number of ion pair produced is lost. However, this proportionality is not lost immediately, but it is lost gradually, and the region between V3 and V4 of this graph is called as the region of limited proportionality. So when we increase the voltage from this graph, as we keep on increasing the voltage from V4 to V5, we see that the number of ion pairs it does not increase much. There is a steady state of increase in number ion pairs. So it is this region is particularly independent of the type and energy of radiation, and beyond the region of V5, discharge occurs throughout the volume of the detector, making it totally ineffective, and there is no counting here in this region. So in this region, the number of ion pairs it increase only slightly with increasing the voltage, and it has reached a saturation which we call it as a plateau. So this is the GM region, that is the Giger-Muller region, and the detector that operates in this region is called as GM counter or a GM Giger-Muller counter. So these counters they produce large voltage pulses, and they are the simplest of all the detectors. So therefore GM counting systems are very inexpensive in nature, and they are widely used for potable radiation for monitoring and counting the gross activity of radioactive elements. Now, the main limitation of a GM counter is its lack of energy discrimination. Also, there are less efficient X-ray and gamma ray measurements. So, to make GM more practically applicable, a end window counter type GM has been designed, which also measures solid samples, and it can also measure the particular, it uses a stainless steel wire, and the characteristics working principle here has been shown in figure 12.9. In figure 12.9, it shows that beyond the plateau how a working voltage is applied, and then the GM counter it measures gamma rays and X-ray. So the working voltage it corresponds to the midpoint of the plateau. The voltage at which the counter starts showing counts is called as the threshold voltage. So here in this plot, the region beyond V5 is called as the discharge region, and in this voltage region, the voltage range is prohibited because it damages the GM tube. So up to threshold voltage it is allowed, that is mostly corresponding to 2400 volts, and beyond that the voltage is discarded because the GM counter is damaged. Now we have also an important concept here in GM counter, that is called as a dead time. So the electrons they travel faster and they form a sheath around the anode, where when in comparison to positively charged ions, because they are heavy in nature, the positively charged ions are heavy in nature, and they do not reach cathode quite fast. So this effectively lowers the potential gradient to the point where the counter becomes sometimes insensitive to the incoming radiations, and this time period is called as the dead time or the paralysis time. So the time period for which the counter does not respond to the next incoming radiation is called as the dead time or paralysis time. So during this time, the counter is not able to resolve between two successive radiations that reaches it. So as a result, the observed count rate, it becomes less than the true count rate, and is correlated as n is equal to m by 1 minus m tau, where tau is the dead time of the detector and is mostly in the order of 100 to 500 microsecond, and this tau is always measured, most of the time it has been measured from experimentally. Now coming to scintillation detector, these detectors, they are based on the interaction of a nuclear radiation, that is with solids where electronically excited atoms are produced. The number of light quanta that is emitted is proportional to the energy of the radiation absorbed, and hence this radiation they detectors, they permit energy discrimination. So typical materials are used as phosphor or scintillator materials such as thallium doped NaI crystals, which are particularly efficient for measurement of gamma rays. So the general construction of a scintillation detector, here it is shown in figure 12.10. It consists of the following parts. The consists of various components. The flashes of the light that are emitted from the phosphor, they are converted into photoelectrons in the photosensitive cathode, and then they enter the photomultiplier tube, which generates a large current. So and then it sends pulses to the respective to pulses to the detector, and the number of pulses are measured. So as this is how a scintillating detector works out. So the scintillating detector is particularly useful for measuring the energy of gamma radiation. Unlike beta particles, gamma rays, they have discrete and well-defined energies. So each incoming gamma ray, it interacts with the detector by one of the following processes. One is the photoelectric effect, one is called the Compton effect, and other is called as the pair production. So by these methods, the gamma radiation, it might react with the skin energy of the scintillating reactor. So now in figure 12.11, we can see the spectrum that is generated from a gamma ray spectrum of a, with its peak position, here it is shown here, and this is how the value for to calculate the resolution, we have this value. Percentage resolution is given as FWHM by peak position into 100. Now for a particular sodium iodide thallium detector, the resolution comes to be around 6 to 8% for gamma rays for cesium 137, and the resolution is also governed by the type of the atoms that is used in the scintillating detector. Then comes the pulsite analysis. So pulsite analysis is a nuclear technique used for distinguishing one gamma radiation from another gamma radiation by measuring the proportionality between the radiation energy and the pulse size. It is used to generate a detailed spectrum, and it undergoes a complex, and it forms a signal. The signal channel pulse height, it utilizes a electronic gate, and it finds the difference between the upper and lower limit. So from this difference in the upper and lower limit, we can find out the pulse height analysis in a scintillating detector. So in order to understand it, analytical applications of gamma spectrum, let us look into this figure that is shown in figure 12.2. Here it is a composite gamma ray spectrum that consists of cesium 137, manganese 54, cobalt 60, and we can see various types of peaks indicating to the different radioisotopes have been indicated here. So in any quantitative analysis, first the area under the each photo peak is measured. So then after the measurement of the photo peak, then if the net photo peak area is calculated given by the equation here in 12.12. So after we calculate this, then the background distribution is removed from the calculation, and then the GN is served to find out the total area of the peak, and that it corresponds to individual radioisotopes. So a GM counter is more sensitive to beta particles, but for gamma radiation, its sensitivity is much less than that of a scintillation counter, because gamma ray is more penetrating and it just passes through the gas in GM counter, in GM tube, and and thus it is not detected by the GM counter. Thus, a scintillation spectrometer should not be used for detection of beta particles. Then comes a semiconductor detector. These detectors, they work on the principle of gas ionization detector. So, and they primarily, it consists of a semiconductor material, mostly a silicon or germanium, and they also has gallium incorporated as impurity, and this is called as we know, this is called as a p-type semiconductor because of the p holes or the positive holes that are available, or they help in the conduction. So on the contrary, if we use elements like P, when phosphorus, when it is introduced in GE, it becomes a N-type semiconductor because it contains the negative sides for conductions. Now an N-type semiconductor, it has higher density of free electrons than P-types, and P-types has a lower density of free electrons. Another requirement for a solid state ionization detector is an element such as lithium, whose atoms are small enough to fit in the interstitial sites of GE. Thus, GE crystal with Li diffused into it, that is called as a GE Li detector, has been most satisfactory. It has been found for the higher resolution of gamma rays. So gamma rays has been particularly, for to understand gamma rays, GE crystal infused with Li, they have been used here. Figure 12.13, it shows a typical semiconductor of GE Li detector. So the resolution of this detector is very efficient to resolve the adjacent gamma rays. It helps to eliminate unwanted gamma rays near the photopeak of interest. Another important parameter that characterizes this gamma ray detector is the efficiency, which measures the fraction of the incoming gamma rays that contribute to the corresponding peak. So here we have in figure 12.14, this is a schematic diagram of a high purity HPGE or GERI detector with liquid nitrogen DIVAR. So superior resolutions of these detectors, they have resolved much more complex gamma ray spectra than that obtained by sodium iodide thallium detectors, as we have shown here in figure 12.15. It shows a comparison in the case where gamma ray spectrometer, scintillation gamma ray spectrometer, here figure 12.5, sharp rays has been obtained, we can see for the GELI detectors, whereas for sodium and sodium iodide in thallium detectors, they show broad peaks. So thus we can say this GELI detectors have been, they can be particularly useful for the analysis of gamma rays. Then auxiliary instrumentation, while using any very high voltage supply, linear or spectroscopy amplifier, pulse height analyzer, these are required. So the high voltage supply must be of high stability and amplifier must have high sensitivity. So therefore the signal is fed through a pre-amplifier to avoid the noise, to go to the noise must be avoided to proceed to the second stage amplification. The first, it involves the avoiding the noise. So it is always essential that the scintillation or semiconductor detector should always be recalibrated using standard sources. Now all the modern instruments, they that are used, they have spectra recording facilities along with the particular software for peak identification, peak area calculation, and for the calibration of the instrument. So modern instruments are well equipped with these features. So now coming to statistical aspects of radioactivity. So in general, any measurement comes with errors. So errors have mostly been declassified into two types, that is systematic or determinate errors, random or indeterminate errors. So the second type, that is the random errors, they cannot be eliminated but can be evaluated by statistical methods as they are random in nature. So radioactive decay, it is a random phenomenon and its measurements are also governed by the certain laws of statistics. It is different from normal analytical measurements where reproducibility is essential. So now if when a radioactive sample is counted, then it is possible to calculate the probability of count rate within certain limits. Every count n, it has an inherent error of plus minus root over n, and thus count rate should always be represented as, it is represented as n plus minus root over of n. This probability can be correctly expressed by the binomial distribution law, but it is a common practice to use the Poisson's distribution law, which is given in equation 12.13. This Poisson's distribution law, it measures to the probability of the errors in the instrument. And since when we look into the probability, the probable error, it expresses the limits within 50% probability, and thus it is given by the equation P is equal to 0.67 sigma, which is equal to 0.67 root over of n. Now the calculation of sigma is easy. So therefore, it is helpful to know that the probability of error decreases with the number of standard deviations. Such kind of calculations, they are mostly made by a rule of thumb for the rejection of unlikely data beyond x bar extending to plus minus 3 sigma. So an error may also occur during a count which might not be due to the random nature of radioactivity, but it might be also due to the electronically or mechanical misbehavior of the counting system. So such counting systems, the for checking the error can be considered by looking into the chi-square that is given in equation 12.16. So while performing an experiment, the chi-square, it needs to be more than, it needs to acquire the chi-square test more than 10,000 counts. It should always be collected in a definite time set counts, and the following determination should be first made, that is the average count, individual deviation, and other the square of deviation should all, the sum of all the deviation should all be nearly zero. The calculation of mean deviation and standard deviation should be made. The relative standard deviation should be done. The mean deviation should be divided by 0.8, and all this, then the number of lines should be counted. So finally, the larger number of observations are made, more precise will be the agreement to the original data. Hence it is always advisable to make large number of observations in order to make minimum number of errors. The background in radioactivity measurements, the background, it plays a important role in radioactivity. So it is defined as the count rate measured in the absence of sample and must be subtracted from that for the sample counts. Background radioactivity, in radioactivity, it may be compared to what we call it as blank measurements in normal conventional chemistry. So it essentially arises from the sources other than the sample. So following principal sources of background radiation may be considered. First is the cosmic ray background. The earth receives a steady stream of high energy particles like from the space. When these interact in the atmosphere of the earth, so we are mainly, then various types of neutrons, mesons, gamma rays are produced. So we are mainly concerned with the gamma radiation that is originated. The nuclear radioactivity in the earth, air, and water. The we know all the reactions, the radioactivity reactions present in the laboratory, they emit the radiations. So also radioactive isotopes are present in natural occurring rocks and minerals. Air also contains certain amount of radon and its products. So even it has also been found that human body contains equilibrium concentrations of radioisotopes like 40K, 14C, and such. So radiations from medical uses, accidental contamination within laboratory, and consumer products have also given rise to increase in radioactivity in the background level. Then comes the major source of increase in radiations, that is from the nuclear power and explosions, which contribute largely to the increase in background radiation activity. It is, however, to actually we cannot altogether eliminate the possibility of background radioactivity. However, some of the discriminations, it may be minimized to some extent, and the minimization is possible by using massive lead steel shielding. We can also use anti-coincidence circuit shield, which consists of an umbrella and it shields the detector and the reactor. We also can use pulse height discrimination. This method will be used, it is particularly useful with proportional counter or scintillation detector in the differential mode. So it is based on the principle that it is that sorting pulses produced by a detector according to its size and accepting only those pulses which are produced by the sample. So these are some of the background corrections that need to be done to reduce the background radioactivity. So with this, the fundamental concepts of radioactivity is over. We'll just take a break of 5 minutes and then continue with different radio analytical techniques. So now coming to different types of radio analytical techniques. So various techniques based on radioactivity has been discovered ever since the discovery of radioactivity was made by natural radioactivity was made by Marie Curie. Then based on the fundamentals of radioactivity, several techniques have been developed, and which are also further newer techniques are being developed. So most of the commonly used techniques that uses radioactivity is the NAA, that is the neutron activated analysis, isotope dilution analysis, which is IDA, radiometric titration RT, radiochromatography RC, radio immunoassay, that is called as RA, and other such techniques with higher modifications, and they are constantly being developed. Now here we will study briefly about various types of radio analytical techniques. Now in general, nuclear analytical methods, they have been classified broadly into two categories. As you can see in figure 13.1, the analytical techniques that make use of nuclear chemistry, or that is radioactivity, they have been categorized by two ways. One is by direct methods, and another that indirect methods. The direct method that includes the direct measurement, that is most measurement of the stable nucleus, that is mostly by we can say NMR. NMR is the direct nuclear analytical method, and indirect method, it uses other activation methods, addition of various radio tracers, use of radiation sources, and various types of other sources, and they are mostly used in NAA, IDA, radio immunoassay, radiometric titration, radiochromatography. These are all indirect nuclear analytical methods. So now we'll start with various radio tracer technique. So this radio tracer technique was first it has been used in various disciplines: chemistry, physics, biology, agriculture, and it was George Devon Hevesy who first discovered the neutron activation analysis, that is NAA, and he won the Nobel Prize for that. He was also the first person to pioneer the use of radio tracers in biology and indicate and also develop the concept of radio immunoassay. So, particularly to define a radio tracer, it is a chemical species or a molecule having one or more radionuclides. That the radionuclide, it might be the cation, anion, or any one of its compounds, so that during the course of a chemical reaction, its location can be marked. So radio tracer is generally called, it is usually associated, it is a radioactive element and which is taken in combination with other molecules that traces to trace the chemical pathway of a particular reaction. The Based on the basic principle on which a radio tracer particularly works is that it mixes well with its own element or a compound, and it behaves chemically in a similar manner, except it has a unique property of its radiation. So radio tracers, they can be used for qualitatively for identification purposes, and they have also been used for markers in various types of reactions. Now coming to choice of particular radio tracers. So it is not possible to use all the radionuclides so as radio tracers. So depending on the type of the reaction and the use of radionuclides, certain assumptions have been made to on the choice of radio tracers for particular reaction. So the most important assumption is that the radio tracer, it should mix perfectly with the system that is under investigation. So it means that the radio tracer should be preferably in the same chemical form as the analyte with which it is being mixed. So it means that the radio tracer, it will behave indistinguishable from the non-radioactive element. So different types of radio tracer, they differ in mass between the active and non-active species. So like for example, if we take 2H and 3H, the isotopic mass effect is quite significant, but the here for other elements the mass is insignificant. So the main criteria for a proper choice of radio tracer are the type of the radiation emitted, the half life of the radio isotope, and also its availability. So there are various factors that influence the choice of radio tracers, and they have been collaborated in figure 13.2. As we can see, there are various factors like that needs to be considered while choosing a particular radioisotope. So one is optimal half-life of the radio tracer, the physiological, the availability and cost, the duration of the amount of activity per experiment, the way, the type of radiation it emits. So all these factors, they have been collated in figure 13.2. So another consideration is that to choose a radio tracer is the type of radiation that is emitted, particularly with respect to the penetrating power, the ease of measurement, and potential radiation damage. So if sometimes an alpha particle is chosen, it is very less preferred because of its low penetration power and associated with high ionization charge and radiation damaging effects. For very thick and dense samples, gamma radiators are used. So thus, looking into the type of the reaction, the type of radio tracers are used. So potential, the chemical and physical interactions of the tracer is also a very important factor. So that generally radio tracers, they are available as chloride or nitrate salt. So the chemical form of the radio tracer, however, it depends on the analyte that we have taken for the system under consideration. So other practical considerations that are very closely available to us is from those are available in BRIT, that is Board of Radiation and Isotope Technology in Mumbai, in BARC. So besides analytical applications, radio tracers have been used for variety of investigations such as leak detection, location of blockages in industrial systems, studies of machine tools and other factors. So radio tracers are also currently, they are used in medical diagnosis and also in agriculture. Then comes to, we'll start with a analytical technique that is called as isotopic dilution analysis, or IDA. So this technique is an analytical technique of considerable value, particularly in complex mixtures of compounds in organic synthesis, biochemical systems, and the determination of inorganic elements. So it was first discovered by George Devon Hevesky, and it has an advantage of not requiring the separation of a component to be determined quantitatively from an analyte mixture. So the method of IDA, it has two alternatives. One is the direct isotopic dilution, that is called as the DIDA, and the inverse or reverse isotopic dilution analysis, that is the RIDA. So the working principle of IDA is primarily based on the specific activity of a mixture of stable and radioisotope. It remains unchanged during the chemical processing. So if we know accurately the specific activity of the radio tracer to the mixture it is added, then we can find out that after the addition of the radio tracer to the analyte mixture, what happens to the resultant specific activity of the total analyte. So then the chemical separation is carried out where the component need not be recovered quantitatively, but it must be chemically well defined from the composition. So here the separation may be carried out by one of the following procedures, like solvent extraction, precipitation using specific reagent, ion exchange, or by electrode deposition. So after equilibrium is attained, the desired constituent is separated and its activity is measured. So how we measure this activity is the specific activity of the tracer element plus it is mixed with that of the analyte mixture. It is equal to the specific activity of the isolated part, where specific activity, it is mostly measured in counts per minute. So in general, the separation is performed by chemical separation methods as here it is listed above. Among all the four processes listed above, the solvent extraction is most widely used because it is quite simple in nature and easy to handle. So here, considering a particular case of example of separation of this radioactive element when it is mixed with a analyte. So we take a radio tracer having a total activity of A per minute and a mass of M star is added to the analyte. So such that the specific activity of the tracer, it becomes A by M star. Now, after the chemical separation, if M1 gram component containing both the active and inactive compound is isolated, then the specific gravity before mixing and after purification is given as S1A and SA1 and SA2. So then, substituting the exact values at the places on solving the equation, we find m1 to be m star into sa1 by sa2 minus 1. So, and from this equation we can further calculate the percentage of the unknown compound that is present in the our analyte mixture. Since all the quantities they can be determined experimentally, here in equation 13.3 the amount of unknown in a given sample can be determined in appropriate units of percentage or ppm. So this is the equation to be followed for direct IDA. So following conditions, however, they need to be maintained to carry out a direct IDA procedure. The radioactive tracer, it must be radiochemically pure in nature. That it must not be contaminated. So the radio tracer, it must be chemically identical with that of the analyte, so which means that it must be ionic or covalent form as the analyte. The radio tracer, it must be uniformly distributed in the sample, so that means stirring must be done throughout the process. Suitable separation procedure must be developed to isolate the component in the pure form, and the half life of the radio tracer, it must be significantly long so as to undergo the whole process of the chemical separation. Now a schematic illustration has been here. It is shown in figure 13.3 of the direct DIDA process, direct IDA. Here it is shown here. Now we also have an alternative method to DIDA, which is called as inverse or reverse isotopic dilution analysis, that is IDA or RIDA. Here in the RIDA, the amount of radioactive substance in the sample, it can be determined by by adding an inactive component, and in this cases the M star is determined by using this equation shown in figure 13.4. So this reverse isotopic dilution analysis is particularly useful for determining the amount of radionuclide which is present in a complex mixture of radionuclides, so particularly in a mixture. So here in one example has been given here, which shows how to calculate the percentage of a particular component in a mixture by IDA. Then coming to the instrumentation of isotopic dilution analysis. So one advantage of IDA is that here it does not require any specific or costly instrumentation, and simple measurements can be made, such as using the Giger-Muller counter or the scintillation gamma counter detector. So since we require a good electronic balance for measuring the accurate mass that is obtained before and after the sample, and for the chemical separation procedure, in normal radiochemistry lab with well equipped globe box and fume hoods are also required. So when the isotopes are used, the dilute natural isotopic ratio is related to the concentration of the amount and isotopic composition of the separated isotope that is added. So in that case, the measurement is through mass spectrometer, and this technique is called as isotope dilution mass spectrometry, IDMS. However, this is very the measurement of IDMS is very sophisticated, and it is not favored much. Coming to the applications of IDA is one of the most widely used analytical technique for trace element analysis in a complex material. So IDA has been used for determination of compounds, particularly that is of industrial importance. Now it has been employed also for several quantitative and qualitative applications also. Some situations have been described here. IDA has been used for quantitative isolation of the element or compound, which is quite difficult. Like for example, it has been used for the determination of iodide in a mixture of halides, as the quantitative separation is almost impossible. IDA has also been used for rapid determination of cobalt in steels using the free radio tracer, the free CO60 of known free cobalt 60 of known activity. IDA has also been used to obtain the entire sample for analysis, like the amount of water or amount of blood present in a particular volume can be determined using IDA. So there are certain advantages and limitations of IDA. So some of the special advantages of IDA are: this is more sensitive than any other analytical technique, and it depends on the availability of the radio tracer that we have taken. While other instrumental methods they fail to achieve complex limits, IDA uses proper radiation detectors, and it can also even measure traces amount of the complex. So radio tracers have potential specificity due to their unique decay properties, and hence their chemical interference are also very little. Quantitative separation is not necessary. However, in many cases, wet chemical analysis that involve radio tracers, it has almost radio tracers has almost been shown to give a yield of 50%. Nuclear detection equipments used for IDA, they are less expensive than many modern instruments. The IDA can be used for speciation studies, in particularly in environmental and biological sample. The decay process of radio tracers, it is not affected by the normal parameters such as temperature, concentration, pH, etc. And besides advantages, IDA has also certain limitations. It is the destructive method since the sample is not preserved. The second is the method can be used for the determination of a single element at a time, whereas for several samples, multi-element methods are preferred. IDA has limited applicability for the elements where suitable radio tracers are available, and blank labels may vary considerable from micrograms to picograms. So these are some of the disadvantages of IDA. Although the advantages are many, we do encounter a few limitations of IDA. So to overcome this certain few limitations of IDA, there is a concept called SIDA. This is called as substoichiometric isotope dilution analysis, and the necessity to determine the specific activity, it makes IDA difficult technique to trace this. So this actually, to overcome this SIDA, where a standard with a known amount of analyte and the unknown solution, they are subjected to an identical separation process. So in this process, same amount of reagent is added, which is a little less than that is required stoichiometrically. So that is why it is called as a substoichiometric process. In both standard and the unknown standards, they are added in substoichiometric amount, and then the analyte is extracted. So here an illustration of the principle of SIDA. Here it is shown in figure 13.4, the substoichiometric isotopic dilution analysis. Since the masses of portion counted here are identical, the specific activities, that is SA1 and SA2, here in equation 13.3, they can be replaced, and finally it is given as the M, the unknown mass of the compound. Here it is given as M calculated into the specific activity A1 and A2 minus M0, where M0 is the amount of activity that is added. So another advantage of this method here is the enhanced selectivity that is caused by competing ability of the unreacted substance towards the impurities. So this technique, it has been widely used for accurate determination of large elements in a variety of complex matrices. Now these methods, they have lost popularity because of very IDA has lost its popularity, whereas SIDA has largely grown popular in determination of with different materials in a complex matrix. Now coming to activation analysis. So the techniques of activation analysis, it include the use of nuclear reactions, and mostly they are induced by neutrons, photons, charged particles like protons, alpha particles, and other heavy metals. So when we target nucleus, it is bombarded with a neutron beam. So a compound nucleus with a higher mass is formed, and it is in an excited state. So it then undergoes a in spontaneous decay to form a product nucleus, and finally emissions like beta or gamma rays are also emitted. So this technique is overall called as neutron activated analysis, or NAA. However, when we bombard a target nucleus with a photon, it is called as a PAA, that is photon activated nucleus. Now, and if we bombard the target nucleus with a charged particle, such as protons, neutrons, or alpha particles, then it is called as CPAA, that is charged particle activation analysis. So now NAA using neutrons, it remains one of the most widely used technique. This technique, it was discovered by George Devon Hevesy, and it is used for the determination of very rare earth minerals using by NAA. So here the principle of NNA, it involves two steps. Basically, the first step involves the irradiation of the sample with neutrons, that is bombardment of the target nucleus with neutrons, and second step involves the measurement of the induced radioactivity. Then the radionuclides that are formed, they are characterized by their gamma ray energy and half life. So here figure 13.5, it shows the schematic of the basic principle of NAA. So here you can see this is the target nucleus. They are bombarded with the neutrons. Then the compound nucleus is, this is the compound nucleus. Finally, the product nucleus is formed. Here the charged particles, the gamma ray, the beta particles and other particles are emitted, and then they are characterized, and finally here you can see the product nucleus is formed. So particularly in this process, the rate of formation of the product nucleus, here it is given as dNp by dt, that is where p represents the product formed, is given as n sigma phi minus lambda n1. So here where in all this equation we can find I is the isotopic abundance, W is the concentration of the element, M is the mass of the target atom, Na here it represents the Avogadro's number. Sigma is the nuclear cross section in barns, that we write it in 10 to the power minus 24 centimeter square, and lambda is the decay constant, where and T half represents the half life of the product. So on integration of this equation 13.6, we find out this equation, which gives lambda n1 is equal to A. This is equal to n into sigma into phi into 1 minus e to the power minus lambda ti, where ti is the time of irradiation. Now since the sample is delayed for time td, so before counting in a counter, so the following equation is obtained, and then it is all substituted with all values, and we find the concentration by this, which is given in equation 13.9. So this way of calculating the concentration of an element using this equation 13.9 is called as the absolute method, where the sigma, phi, ti, td and epsilon, they are measured from experiment. So after calculating W, here from equation 13, after calculating W, the concentration of an element in the sample, its mass is determined. So however, the absolute method has certain uncertainties in the values of sigma and phi. So in order to eliminate the uncertainties in the absolute method, a comparator method, it has been suggested, where a primary or a secondary standard is taken and its concentration is compared with that under the experimental conditions. So both the parameters are counted using the same detection system, and finally an equation here in 13.11 it is obtained, where a by a dash is given by the following equation. So this equation is only applicable if t half of the radionuclide, it is comparable with the delay time and the counting time. So however, if the t half is long enough compared to td and tc, then it is further simplified to equation 13.12. So where many elements, they can be determined using this formula. Now in equation 13.12, the activity is replaced by specific activity to have a uniformity while considering the sample and the comparator. So the standard or the certified reference material, that is the SRM or CRM, they are actually available from various standard agencies like the NIST, the National Institute of Standards and Technology USA, the International Atomic Energy Agency, that is IAEA in Vienna, the National Institute of Environmental Studies, NIES in Japan, Institute of Nuclear Chemistry and Technology, INCT in Poland, where the RNs, that is the reference materials of a variety of matrices such as plants, tissues, or dust particles, rock, solid, powder, and all are available. So therefore, but these are very expensive in nature. Therefore, many laboratories they prepare their own standards from various grade salts, that is from the analytical grade salts on SiO2 cellulose or Hartmann paper filter strip. So that is why a standard is always necessary to know the concentration of the element present in our mixture. So in order to achieve a better accuracy and to eliminate the errors due to a secondary standard, a mono standard method has been proposed. So in this method, in the mono standard method, this equation 13.13 has been used, where multi-element NAA has been performed. And from this equation in 13.13, the a k0 factor here it is obtained. So the k0 factor, it is an experimentally determined value that contains the values for the nuclear constants. So and finally, after utilizing the k0 factor, a k analytical factor has been obtained and is given in equation 13.14. So the k0 factors, it has for is different for different nuclides, and it is published using gold as a comparator element. Now coming to different neutron sources in a NNA. So a wide range of devices is used to produce neutrons that is required for the NNA. Some are very expensive in nature while others are very simple in nature. So here in figure 13.1, some common sources of Na neutrons for required for NAA is listed below. So for isotopic sources, the photoneutrons, these are used in machine type. For machine type sources, these are the neutrons that have been listed, these are the instrument that produce neutrons. And for nuclear reactors, neutrons are provided from the nuclear reactors like Apsara, Circus, Dhruva, Mumbai in Bark, and Kamini nuclear reactor in that is in IGCAR Kalpakam. So these are some of the common sources from which we obtain neutrons to carry out NAA. These neutrons, they are good for demonstration experiment and also for the demonstration of major constituents such as aluminium, magnesium, copper present in an alloys. However, these neutrons, they have limited half-life and they are not good for trace element analysis. So on the other hand, machine type sources, here they have the advantage of being put off and not in use. So neutrons may be classified on the basis of energy. So first is thermal, which have 0.025 electron volt, epithermal neutrons, where the energy ranges 1 eV to 1 keV, and fast neutrons, where the energy is greater than 1 eV. So various activation methods have been developed using these three types of neutrons. Now the energy of the neutrons is also important because they are used for different types of reactions such as N gamma, NP, N alpha, N dash. These are some of the possible reactions depending on the type of the reactions employed. So here in figure 13.17, a schematic layout of the production of 14 MB fast electrons that is produced in a Cockcroft-Voltron neutron generator that uses DTN4. Here it is shown here. So this is just a diagram of a 14 MeV neutron generator. First, then coming to the different classes of neutrons. First is for employment of thermal neutrons in thermal NAA. The thermal neutrons, they have an energy of 0.025 electron volt and they can induce radiative capture, that is N gamma reactions in the target nuclei, and the delayed gamma reaction rays from the sample are detected. So here TNNA, it offers potentially higher sensitivity for a large number of elements, but it is not sensitive for lighter elements like C and O. TNAA, it can be used, that is the thermal neutron activation analysis, can be used for the determination of concentration of to 60 elements. Then comes epithermal neutron activation analysis. It employs epithermal neutrons who have the energy in the range 0.1 to 1 ev. In practice, the lower end of the neutron energy here, it is closer to zero point 0.5 ev, so which is the cutoff energy, and the higher end of the energy, it extends through the resonance neutrons up to several keV. Epicadmium neutrons, they are induce N gamma reactions, and they are used as detector for many elements. So these elements, neutrons, they have limited practicability and they can be determined for ytterbium with higher sensitivity. So fast neutron activation analysis, it employs fast neutrons which has an energy range of zero point 0.5 to 20 MeV. So neutrons of this range, they do not induce any N gamma type of reactions, but rather they induce N proton, N alpha, N dash, and N2N types of reactions. So mostly these fast NAA reaction is performed using 14 MeV neutrons, and they are particularly useful for the determination of oxygen using this reaction. So here an illustration of a 14 MeV neutron generator has been shown in figure 13.7. Now coming to interferences. Since nucleon NAA activation analysis is based on nuclear phenomena, hence no chemical interference are possible. But nuclear interferences of primary, secondary order, gamma ray spectral interferences, neutron self shielding, gamma ray self attenuation, and other such interferences may occur. So some of the interferences are like the primary interference. This interference, it arises when the same radionucleotide, it is formed from an element which is other than the analyte element. Like for example, if we take 56Mn, it is produced by N gamma reaction. The same radionucleotide is also produced by 56F NP reaction and cobalt 59 N alpha reactions. Okay, so this, the determination of Mn in steel that contains iron and cobalt may be full of error if high energy neutrons are present. So this is what is called as primary interference. So other examples of such interference are in the determination of aluminum in presence of silicon and phosphorus in soil, or sodium in presence of aluminum and magnesium in biological samples. Then coming to spectral interferences. Gamma ray spectral interferences, it occur when similar gamma ray energies are produced by other radionucleotides by other elements. For example, if this much energy of 56 Mn is often interfered by 844 kilo electron volt of 27 Mg. So in such cases, other indicator gamma rays, it should be used, or one should wait for the decay of the other radionuclide. So other types of less common interferences, these are due to successive capture and secondary particles that arise from primary reaction. For example, in the reaction of manganese by N gamma reaction with that produces 56 Mn, it is also produced by a successive reaction of these. Similarly, when determining nitrogen in different species, these type of spectral interferences also occur. Then coming to sensitivity and detection limits in NAA. The sensitivity of an element in NAA can be defined as the counts for particular experimental conditions like the irradiation, the delay, the counting duration, besides the influx, the neutron influx of the irradiation source. Depending on the nuclear properties such as isotropic abundance and absorption cross section, neutron cross section, that is sigma. So we, these parameters, the sensitivity can all be decided. So from the activity equation 13.58, we know that the main parameters for sensitivity are the sigma, the phi, and epsilon. Now since the cross section, that is sigma, that is fixed for a target nucleus, it cannot be changed. The high flux neutrons and a detector of high efficiency is needed. So therefore abundance, that is I, it plays a much important role in deciding the detection limits of the instrument. So the rate of activity of a radionuclide, it depends on the flux, neutron flux, and the time of irradiation, that is Ti. So for a particular target being irradiated in a device, the activity it increases exponentially. Here it is shown in figure 13.8. The variation of activity with neutron flux which increases with time. So a comparison of all the three activities has been shown. So it is observed that the highest activity is obtained for irradiation with a very high flux reactor, as it is shown from this graph. In NAA detection, limit varies from Pg to Mg depending on the type of the element that we have used, the depending on the type of the gamma ray background, and the sample matrix. So detection limit, it is actually a statistical concept, and it is based on the availability of the measurement method. So without a precise statistical definition, it is impossible to determine a numerical value for the limit of detection, that is called as LOD. So in general, all LODs, they have been defined in terms of 3 sigma, where sigma remains the standard deviation for all the samples. Thus, the detection limit is defined as the 3 sigma of the standard deviation of the background counts and the peak, that is, and under the peak, and is calculated giving the equation in equation 13.5. So this equation, it shows the calculation of a detecting limit, that is LD. The counts here, they are then converted using sensitivity as mass. Also, the activity here may be taken as 10,000, which records with 0.1% statistical error under experimental conditions. The typical detection limits using a flux of 10 to the power 3 Newton per centimeter square second, they are available. This is the reported data in literature. Then other conditions, sensitivity can also be improved if RNAA procedure is followed and the background is lowered. The classification of NAA technique. The NAA technique can be broadly classified as instrumental and radiochemical NAA, depending on whether the sample is counted directly after irradiation or after chemical separation. So many methodologies have been developed for this place, and this has led to instrumental advantation and other data processing procedures. Some the Here in figure 13.9, the various methodologies it has been shown. The first is PGNAA, that is the prompt gamma neutron activation analysis. So in this methodology, prompt gamma rays that is emitted during N gamma reaction, they are counted. So an essential feature of this technique is that the detector system has to be placed in close vicinity of the irradiation so that gamma rays are directly counted. So measurement of gamma rays should be is all critical in this PGNAA procedure. Now, so here this is most clinical use lies in the in vivo determination of B10 concentration that is needed to measure the radiation dose received by patients during cancer therapy. Then is short irradiation activation analysis. This involves the irradiation of the sample for a very few short duration like 1 to 600 seconds and a counting after a delay of 20 to 100 millisecond. It is particularly useful for the determination of elements which has a very short half life in the order of few seconds. The advantage, it has a good advantage of a very low turnaround time, and it has a high throughput. A fast irradiation measurement system, that is FIMS, using TRIGA Mark II has been developed. The short instrumental NAA with high throughput, sensitivity, and accuracy without metric interferences can be achieved in spite of all the high count rate and low and long lived nuclear activation. Some typical examples for this case has been shown here. The third case is cyclic neutron activated analysis. This is CNAA. In case of elements that with short-lived activation products, the sensitivity is hampered. So this difficulty is overcome by repeating the whole cycle of irradiation and then counting several times. and then particularly summing of the gamma ray spectra, as here it is shown in figure 13.10. This shows a schematic depiction of the cyclic neutron activation analysis, and you from equation 13.16 the total activity it can be measured. So for any significant counting counting, a typical example for this technique has been with the determination of aluminum, which is mostly done by CNAA. Then comes the derivative NAA. This method is also called as molecular activation analysis and is used to enhance the sensitivity of NAA for more elusive elements. So it has the advantage of being useful for studying chemical speciation. In this technique, an element or a chemical that is the unknown quantity, it is first complexed with or exchanged with another element which has a higher sensitivity for NAA. So then from it is after the product is formed and the radionuclide removing the interference from the background, then the determination of the activity is calculated. The fifth is in vivo NAA. It is suggested that NAA it can be used to determine whole body elemental levels in organisms. Now, this has particularly been used in nuclear medicine and biomedical analysis, and these are some of the equations in vivo applications. The fifth is chemical treatment before irradiation. In some cases, chemical separations are required before irradiation as a special measure because the concentration of the analyte is too small and it is difficult to measure them. So this is often required for CNNA. The following types are involved. Pre-concentration NAA. It is especially useful in case of water samples because of low levels of analytes present at the levels of micrograms, nanograms, or even picograms. Then is CNNA. It was developed for determining trace amounts of analytes such as arsenic and mercury in variety of matrices that also includes rocks. Then is speciation neutron activation analysis. This is SNAA. The chief elimination limitation of NAA is that it cannot be used for speciation studies. However, its scope is extended for speciation studies by this process. So, to first, this is essential because there is an increasing interest in studying speciation by NNA and to understand its low detection limits. This process it involves two steps. First, the separation of the species is done, followed by detection of element by NAA. So, variety of methods it involve liquid chromatography, reversed phase chromatography, or ion exchange that has been used for the separation of various organic, inorganic, and organometallic species. The main advantage of SNAA, it includes simultaneous speciation of elements such as chlorine, bromine, and iodine, which are very difficult to be determined by other techniques. A SNAA method has been developed with in combination with HPLC for the determination of low levels 5 arsenic species that can be detected in natural water. Then coming to instrumentation of NAA, the general procedure of neutron activation analysis can be divided into various stages, such as which include the sampling, the sample packing, irradiation, the type of irradiation, and thus the new it has been and the source of neutrons. So most widely source of neutrons that we have also studied, they can be obtained from Brit Mumbai. The gamma ray spectrometer it actually forms the basis of NNA, and here the utility of this in figure 13.11 we can see the schematic of a high resolution gamma spectrometer, that is the heart of NAA analysis, that is neutron activated analysis, is solely dependent on the type of the gamma ray spectrometer that is used. Here it consists of a HPG detector with all its electronic accessories, and it has been shown in figure 13.11. So the characteristics E gamma, T half, and other characteristics that are studied by NAA, they have been shown here in table 13.2. figure 13.12, it shows the a gamma ray photographic representation of a HPGE that is used in a laboratory. Figure 13.13 and 13.14, it shows the typical gamma ray spectrum of the radionucleotides in present in neem leaves. Then calculation and data processing. So for the data processing here, importance, mostly it is done in a Gaussian the Gaussian distribution is obtained and various types of software has been used, and the important steps that are computerized for needed, that is for analysis of photo, that involves smoothing, peak searching, selection, peak energy calculation, and then followed by peak area calculation. So figure 13.5, it shows the from a total peak area, how do we calculate the total peak area from the region of our interest. And however, this can be mostly done with specialized software that comes in attachment with the instrument. Now the applications, various applications of NAA has been shown in this figure. It is used in geology, environmental applications, biological applications, forensic applications, and in other various in the determination of trace elements in various sectors. The advantages of NNA is that it is now universally applicable for determination of trace element. It is actually devoid of any chemical interference. It is highly specific, and the low detection limits can be used for detection of many elements. It is non-destructive in nature. Although it has many advantages, NAA is also has certain limitations, like it requires a nuclear reactor. It is less cost effective. However, no so it is sometimes elements like lead cannot be detected, and it cannot be automated after irradiation. Now here a comparison is shown between NAA and IDA with other trace elements in terms of its other analytic experiments in terms of accuracy, sensitivity, distribution, multi-element sample analyzer type, the sample type. Here in this table it has been listed. So isotopic dilution is particularly, we can say, it is a destructive analytical method, and the sensitivities of IDA is often restricted. So whereas on the other hand, NAA, although there are limitations of NAA is far more sensitive in comparison to IDA. So then comes radiometric titrations. So these are based on the detection of radioactivity in separable species during a titration process that indicates the endpoint. Here, no. First, a radio tracer, it is added to the titrant or the unknown analyte. The sole purpose of the use of radioactivity is for detection of endpoint, and as such, it does not participate in the whole titration process. So, in figure 13.17, we see a typical experimental setup for radiometric titration. Here, a syringe is used to move the supernatant solution in and out of the counting chamber, that is a scintillation detector. So mostly a typical example of radiometric titration has been in the determination of halides using silver 110 as a radio tracer element, where corresponding silver halide is precipitated. Other experiments have been also been identified using radio isometry. Here, alternatively, advantages and limitations of RT. This method has an advantage that the detection of endpoint does not depend on the chemical reaction. So, in principle, any titration where a phase separation is present, it is affected, it is good for radiometric detection, provided we use a suitable radio tracer. Now comes radiochromatography. Radiochromatography is based on paper or TLC, that is thin layer chromatography, though it could also be used for ion exchange column or gas chromatography, as well as in electrophoresis. Here, a radio tracer as a cation or an anion or a radio labeled organic compound is used. Thus, any chromatographic separations can be used using radio tracers. However, no chromogenic reagent or detector is used to study of the initial spot except the nuclear containing equipment or the radiographic element. So here the distribution of activity measurement is very sensitive, and it is sometimes it is difficult to study the activity simply just by looking at the spot movement. Radiochromatography, it plays an important role in the discovery of some transplutonium elements. The identity of element of 5F series was established beyond any doubt by the sequence of their analogous corresponding 4F elements, and this is one important example of use of radio chromatography for analytical purposes. Now let us consider a typical example of separation of alkali metals using respective tracer solutions. So here, by using proper asbestos paper that asbestos paper that contains a radio tracer element, that is the scintillation gamma ray spectrometer, which is made with sodium iodide in thallium. So we can, looking at the activity of the particular alkali ions, we can identify the actual ions that are present in the determine the actual ions are present in the analyte. Then comes radio immunoassay. It is a particularly useful for assessing biological molecules, and they are mostly used in determination of hormones, vitamins, drugs, particularly in biology, drugs, viruses, and other such substance, organics, biological species. Now it is based on the working principle is based on the specific reaction between an antigen and an antibody, and by using a radio labeled antigen that is represented as Ag star. So an antigen, it is a biomolecule, and it should be able to react with the antibody, which is a complex protein. So for example, if a living system it encounters a new virus which causes a disease, it will try to resist the virus. So one mechanism of virus is resistance of virus is by the activation of the antibodies. So the antibody then binds with the antigen to form the antigen antibody complex. Here it is, as here it is shown. Now once the antigen is bound to the antibody, the virus is no more active, and thus it is excreted from the body. So this reaction of the antigen is highly specific, and thus by using a particular radio labeled isotope such as Ag star, we can trace the antigen antibody complex and know its activity, determine the activity in the biological pathway. Then here, figure 13.19, it shows the principle of radio immunoassay that is performed to understand, to determine the exact concentration. Here in, as we have shown in figure 13.12, the plot of the radio immunoassay is shown, and from this curve we can determine the concentration, unknown concentration of the antigen by counting by looking at the activity of the Ag star AB complex. So here mostly radio labeled antigen, that is Ag star, has been used, and the most commonly used has been the I-25. I-125 and I-131, that is the radioisotopes of iodine, are commonly used. So the applications, this radio immunoassay, it has various applications, like particularly mostly in biological samples. It has been used for analysis, selection of various uh, compounds by RIA. So analysis by RIA, it does not require any sample preparation. The samples may be collected at remote places, and in table 13.4, a selection of the compounds is listed. Those have been analyzed by RIA, various drugs such as diazepam, gentamicin, morphine, nicotine, steroids such as androgens, estrogens, corticosteroids, and various polypeptide hormones like FSH, follicle stimulating hormone, glucagon, growth hormone, insulin, etc. They have been analyzed by the process of by RIA. Thus, in summary, we can say that RIA is a very developing and highly essential technique for medical diagnosis. So, with this, we end the session of radio analytical techniques. If there is any question to ask, please ask.
No, ma'am.
Okay, then thank you for today's class. Thank you.
Thank you, ma'am.